Okay, hello. Welcome to the New York City Category Theory Seminar, February 17th. Rick Blute of the University of Ottawa is speaking. Fire away.
Thanks, Nosen. Yeah, so my talk tonight is, I'm going to describe several papers, at least one of which is ongoing. And the subject is finiteness bases. And Nosen suggested that maybe, sorry, let me back up a second. Finiteness spaces arose in the proof theory of linear logic, specifically the categorical proof theory of linear logic. And since that might be something that not everyone is super familiar with, I thought I'd spend some time just talking about that, even though I'm not going to use any ideas from linear logic itself in the talk. So if I had to describe linear logic to somebody, I would say it's a logic where conjunction behaves like the tensor product of vector spaces as opposed to the Cartesian product of sets. So let's unravel that idea and see where it comes from. And the idea goes back to the subject of categorical proof theory, which was introduced by Jim Lambeck. And Lambeck's idea was a great one, and it's still in regular use today. And the idea is pretty straightforward. Given a logical system, what I'm going to do is I'm going to build a category, and the objects of my category are going to be formulas in that logical system, and an arrow will be a proof. And strictly speaking, that's not correct because I need to mod out by some equivalences to make everything work out right, but that's the principle. And so an arrow F from A to B will be a proof that A logically entails B. So in particular, to do this properly, you need to develop the theory of formal deductive systems and so on. And that's what the project that Lambeck started in those early reports of the Midwest Category Theory Seminar Springer lecture notes. And when you do that properly, what happens is your logical connectives become functors, and that category of proofs becomes the free category of an appropriate type. So let's actually look at an example of this. So let's take a look at the logic of conjunction, implication, and true. So conjunction will be interpreted in this logic as the categorical product. And so that means in particular that I have morphisms from A and B entails to A, and from A and B to B, and A to A and A. So these are the standard projections and the diagonal associated with categorical product, but now they take on a logical meaning. So now the first one says that A and B logically entails A, as you would expect. And the third one says that A logically entails A and A. So they now have a totally different meaning from this viewpoint. Implication will be interpreted as the internal hom. And so in particular, my implication will have a co-unit. And that co-unit is a map from A and A implies B to B, which is on one hand the co-unit of the adjunction, and on the other hand the modus ponens rule from propositional logic. And T will be interpreted as the terminal object, since everything implies true. And so if you build up your logical system properly and you introduce the appropriate equivalence relations on your proofs, then the result will be the free Cartesian closed category that's generated by the atomic formulas. And there's several ways to go about this. You can denote your proofs using the simply typed lambda calculus, or you could just keep track of the proofs themselves. But in either case, what you get at the end of the day is the free Cartesian closed category generated by the atomic formulas. So I think this is an incredibly neat idea, and it's really a good way to think about free categorical structures, and at the same time, a good way to think about various systems of propositional logic. And once you have that system set up properly, then categories with that appropriate structure all become models of the logic. So you can model propositional intuitionistic logic is a technical name, but in categories like categories of sheaves and pre-sheaves and similar categories, any Cartesian closed category that you want. And you can view those categories as models of logic, which frequently gives you some interesting ways of thinking of those categories. So linear logic changes the game, and it changes the way we think about logical entailment. So instead of interpreting logical entailment as the premise implies the conclusion, we're going to imagine that we have a machine. And in that machine, I can input a token. And then the machine outputs that token, outputs a token. And so we'll now view the premises as the inputs into a machine and the conclusion as the outputs of that machine. And from this point of view, those three rules I showed you a second ago are completely wrong. So A and B logically entails A. Now this says I put an A token and a B token into my machine and it only spits out an A. So that's very logical if you own the machine, but as a logical principle, it's off. And similarly, the third one doesn't work anymore either. It says I put one token into the machine and it spits out two of the same tokens. And so the first step in understanding linear logic is to eliminate those three rules from your logical system. And the result is, in the first place, there's a lot more to it than this, but in the first place, you wind up with a logic that behaves much more like where the conjunction behaves much more like the tensor product of vector spaces as opposed to the Cartesian product of sets. And that's what I said there. And so you can still have implication. So the result is a symmetric monoidal closed category. And when you mod out by the appropriate equivalence relations, again, you in fact get the free symmetric monoidal closed category. So as I said, I think this is an excellent way of thinking about logic in free categories. And when I first read the book by Lambeck and Scott called Introduction to Higher Order Categorical Logic, I thought, you know, every logic that I ever come across, I'm going to apply this process to it. But there's one logic where this doesn't work at all, and that's classical logic, unfortunately. The logic that everyone uses in their everyday lives, this doesn't really work. And I'll show you why on the next slide. But the problem in a word is negation. But that problem doesn't come up in linear logic. We can do negation without any trouble at all. And that's what I want to show you next. So imagine we have a symmetric monoidal closed category. We'll say it's star autonomous if there's an object which we'll call perp or bottom, such that the canonical natural transformation, so this is the translate of the co-unit of the injunction. So that exists in any symmetric monoidal closed category. So I have always a map from A to A implies bottom. I require that map to be a natural isomorphism. This definition is due to Mike Barr, and he was inspired by various categories of topological vector spaces, one of which, time permitting, I'll mention towards the end. And when his book first came out, his Springer Lecture Notes 752 or 3, there wasn't much interest in it until somebody noticed that this corresponds precisely to linear logic. So, as I mentioned a minute ago, classical logic doesn't work. And so if you tried to model classical logic in sort of the naive way that I've been suggesting, what you would say is the following. I'm going to say that not A is, as it is defined in traditional propositional logic, the same thing as A implies F. And F is typically modeled by the initial object because false implies everything. And so what I would try to say is a classical category is a category that's Cartesian closed, has an initial object such that this map here, the map that goes from A to A implies F, that's an isomorphism. And that seems like a great definition, but it kills the whole subject because there's a theorem of André Gioia that says that a classical category is just a Boolean algebra up to equivalence. So what you've done in this naive way of thinking about classical negation is cause all of your different morphisms, your different proofs, to collapse into one proof. So not a good idea. Now, there are clever ways to get around this, but this naive idea just doesn't work. But as I said, in linear logic, it works fine, and everything is fine. And there's lots of star autonomous categories in the world, some of which are standard. So finite dimensional vector spaces. It's a symmetric monoidal closed category. You can take the dualizing object to be the base field, and so negation just simply becomes the dual space. And of course, it's a standard result that every finite dimensional vector space is isomorphic to its second dual, and so therefore that's a star autonomous category. There's an example that we use all the time in sort of the computer sciencey applications of linear logic, and that's the category rel of sets and relations. So your objects are just sets, and a formula is a binary relation, so a subset of x cross y, and I use relational composition to compose them. The Cartesian product of the sets gives me a tensor product, and that category is also star autonomous. In this case, the dual object is just the singleton set, and in fact, x perp is just the same thing as x in this case. A more interesting example is complete soup lattices. So this was, in fact, if you read the book by Gilles and Tierney, The Extension of the Galois Theory of Grothendieck, they use the star autonomous structure of that category quite freely in that book. And there's also, as I said, various categories of topological vector spaces. So in particular, there's a class of vector spaces called linearly topologized spaces. These were introduced by Solomon Lefschetz. And the idea here is it's obvious that a infinite dimensional discrete vector space, its second dual space, is a significantly larger object. And so the idea was, if you add topology and define dual space to be linear continuous maps, then perhaps you will cut down the size of the dual space to an appropriate extent that you can recover infinite dimensional vector spaces that are isomorphic to their second dual. And that, in fact, is exactly what happens. And that was first noticed by Lefschetz. And this is one of the categories that led Bart to write down the definition of star autonomous category. Okay, so I realize I'm probably getting myself in some trouble here because this is being recorded. And if someone was malicious, they could mail this to France and get me in huge trouble. But I wanted to show you something that I think this is pretty funny. The strangest symbol in mathematics. So in classical logic, you can define disjunction by Demorgan duality. So not A and B is the same thing as not A or not B. And anytime you have a classical logic, you can do this. So in particular, I can define a linear version of disjunction, which would be defined as by this Demorgan-like rule using the linear tensor, the linear conjunction, as opposed to traditional conjunction. And if you've never seen this before, you're about to be surprised, because what Ehrhard did is he denoted this by an upside down ampersand. So the first paper on linear logic came out in 1987 when LaTeX was just coming into being. So upside down ampersands were a real problem. But these days we have text symbols for it without any fuss at all. The only reason I mention this is what we want are star autonomous categories which don't satisfy an equation that looks like this. Because if A tensor B parentheses star is A star tensor B star, then you have a model of your logic, but and or are treated the same, which isn't really a very good situation. And so in particular, finite dimensional vector spaces and plain old ordinary relations are not interesting as models of logic. And by the way, the experts in the room will realize this slide is a double joke, because question mark and exclamation point are also symbols of linear logic. Okay, so the example that I want to show you of a star autonomous category, which does not satisfy this bad equation, is in fact a category of decorated relations. And a lot of examples of star autonomous categories satisfy that. And these are called finiteness bases, and they were introduced by Thomas Ehrhard. And you'll see that the morphisms in the first version that we're going to talk about are really just relations where we've added some extra stuff to prevent this isomorphism that we don't want to hold. So we're going to start with a set X, and we're going to let U be, this fancy script U, be a set of subsets of X. Then I'm going to define U perp by U perp is going to be all those subsets U prime such that their intersection with all the U's in U is a finite set. So I'm going to leave that there for a second for you to stare at, because it takes a minute to parse this. right? So if you give me a set of subsets, I'm going to take every subset for which its intersection with everything in that U is finite, okay? And that's U perp. Let's just do one simple example. If I take U to be everything, then U perp is just going to be the finite subsets. Conversely, if I take U to be the finite subsets, then U perp is going to be everything, okay? We'll see more interesting examples than that as we go forward. And so here's a lemma about how things work with this perp operation. So U is always contained in U perp perp. And if U is contained in V, then V perp is contained in U perp. And U triple perp is the same thing as U single perp, which obviously you can show immediately from the 2 bullet points above that. Then what we're going to say is that a finite space is a pair, X U, where X is a set and U is a subset of P of X, such that U perp perp equals U. Okay? Sometimes I'll denote X by absolute values of X, the underlying set, and I'll denote U by F of X. The elements of U are called the finitary subsets, and the elements of U perp are called cofinitary subsets. And as I said, as we go forward, we're going to see a bunch of non-trivial examples. So is that okay with everybody? I can keep going? Okay.
Good, good, good. Very good. Thank you. Go on, go on.
Okay. So morphisms are going to be relations. So a morphism of finiteness bases is going to be a relation such that if you give me a finitary thing in X and I relationally compose it with R, I get a finitary thing in Y. And going back in the opposite direction, if you give me something in F of Y perp and I compose it with R to get back, I precompose with R to get back into X, that has to be in. So going forward, finitaries go to finitaries, and going backwards, cofinitaries go to cofinitaries. Okay? Composition is a relational, and it's pretty easy to verify that this is a category, and we'll denote it by fin-rel. And so the theorem is it's a star autonomous category, and it will turn out as you calculate some examples that it's not, it doesn't satisfy this unfortunate equation here. Okay, the tensor product is defined by you take the Cartesian product of the underlying sets, just like you do for ordinary relations, and there's a choice for f of x tensor y that makes this work. And the choice is you take all the squares, so the product of a finitary thing in x and a finitary thing in y. So you take all those squares and then you downward close that set. Okay, so you can check that that's a finiteness space and it acts as the tensor product, and this category is symmetric monoidal closed, and the 1-point set acts as a dualizing object. So this is a really nice example, and Thomas and his student Christine Tasson have proved all sorts of properties about finiteness spaces, and they've used it to prove all sorts of things about various extensions of the lambda calculus. So there's all sorts of interesting stuff that you can do with this category. This is just a remark for the experts who know about all of linear logic. So this category is a full model of complete linear logic. So the part I mentioned in the slides above is really just a small fraction of the whole thing. So in particular, it has a comonad on it, which we denote by an exclamation point, and it has a monad by duality, which we denote by a question mark. And these have to satisfy all sorts of properties. In particular, the co-Kleisli category of the comonad has to be Cartesian closed. So there's a nice relationship here between the monoidal logic and the Cartesian logic. And various equations have to be satisfied that are implied by the proof theory. And we call it, when we have one of those, we call it a Seeley model, named after Robert Seeley, who wrote the first paper on this structure. And so I'm not giving you any details because they have nothing to do with what I'm talking about, but all of that structure is there. Now, Ehrhard was trying to build models of linear logic. And so therefore, relations were clearly the correct choice of morphism. But what if we wanted to do something besides the linear logic? We wanted to use finiteness spaces for other things. So there's several different choices we could take. Suppose we took functions to be our morphisms. And we said, we're going to take a morphism in our new category will be a function between the underlying sets of x and y. And it still makes sense to require that these two properties hold, so that the forward image of a finitary in x is a finitary in y, and the backwards image of a cofinitary in y is a cofinitary in x. So you can do that, and we get a category which we call finf, and it's still not particularly satisfying. So the problem with relations from a point of view of a category theorist is that that category is lacking all sorts of limits and colimits. It has all the products and all the coproducts, but it does not have much in the way of equalizers. So finf, unfortunately, still doesn't fix that. It's symmetric monoidal, but it's not closed. And it also doesn't have a terminal object. So still not the right choice. It turns out that the right choice is partial functions. So our category is going to consist of finiteness spaces as objects, and a morphism will be a partial function from x to y, which satisfies those same conditions that I mentioned on a previous slide. And the result of that is a category which is symmetric monoidal, closed, complete, and co-complete. So this is the category we want to work in. And the first application is I want to show you that this gives us a really coherent way of thinking about a construction of Ribenboim of generalized polynomials. So Ribenboim, you'll see the construction in a minute. Why don't I just get to it? You get a rich class of rings by its construction, but it seems like it's not terribly motivated. What we're going to show is that finiteness spaces are a motivation of it that works perfectly. So this is just review for everybody, but we know that when you want to multiply power series together, you have to be worried about infinite coefficients showing up. So if I try to multiply a series which goes all the way from minus infinity to infinity by another such series, you can easily wind up with infinite coefficients. And there are multiple solutions to that. One is to bound any series from below, in which case you get Laurent series, and thereby ensuring that the product of two Laurent series is well defined, because the sum, the number of terms which add up in any given term in the product, is finite. And so we're going to define this operation here, x sub m of fg, to be all those pairs. So m is just a monoid here. All those pairs such that u plus v adds up to the fixed m, and f on u is not zero, and g of v is not zero. And so it's clear that for the product of two series to be well defined, I need this set here to be a finite set. And that was Ribenboim's realization. So here's how he did that. So again, the point is to ensure that this set here, this indexing set, is finite. So here's his approach. So I have a partially ordered monoid, and I'm going to say that it's strictly ordered if the multiplication, or I guess in this case the addition, preserves strict inequalities. And then we'll say that an ordered monoid is Artinian if, in fact, this has nothing to do with the monoid structure, if all the strictly descending chains are finite. It's narrow if all the discrete subsets, so a subset is discrete, meaning it's discrete when its order is restricted to that subset. So it's narrow if all the discrete subsets are finite, and it's Noetherian, I didn't put this on the slide for some reason, if every strictly ascending chain is finite. Let's let A be an abelian group, and we'll say that if I have a function f from M, a monoid to A, we'll say that its support is all those things in M which don't get sent to zero. Then the space of Ribenboim power series from M with coefficients in A is just the set of functions from M to A where the support is Artinian and narrow. And we'll call that guy G of MA. And so G of MA is going to be a ring. If A is a K algebra, it's a K algebra, but in particular, it's a ring. And the multiplication is defined by F times G applied to M is going to be F of U times G of V such that the properties I described a minute ago hold. So F of U is not 0, G of V is not 0, and U plus V adds up to M. So that's what this formula here is saying. And this will be well defined if I can prove that this set, XM of FG, is in fact a finite set. And Ribenboim shows it's finite. The proof is just roll your sleeves up and do it. But when you do that, you get all sorts of examples. You get Laurent series, you get usual power series, you can get just plain old polynomials, and many, many more examples. And I refer you to our paper, which is now out, for a bunch of other examples. But here's what I want to point out, and that is this notion of Artinian and narrow seems fairly random, but it isn't. And the motivation can be seen coming from finiteness bases. So let P be any poset. This has nothing to do with the monoid, the operation. And sorry about that, I can't turn that phone off. Let U be the set of Artinian and narrow subsets, then P of U is a finiteness space. And in particular, U perp in this situation is going to be the Noetherian subsets of P. Okay, so that now explains where Ribenboim's conditions comes from. And I'm actually a bit behind where I want to be. So we'll say that P and Q, if P and Q are posets, a map between them is strict if it preserves strict inequality. And that's a category. And so this functor E, this operation E, which I didn't call it E up above here, which takes a poset to the corresponding finiteness space, is a strict symmetric monoidal functor. Okay. And since it's a symmetric monoidal functor, it takes monoids in the first category to monoids in the second category. And so we'll say that a partial finiteness monoid is an internal monoid in the category of finiteness spaces and partial functions. Okay, so how do we get the ring structure that Ribenboim got? So we're going to use an operation that's due to Ehrhard again, and we called it linearization. So if you give me an abelian group and a finiteness space, I'll say that I'll define A bracket X to be all those functions from X to A, such that the support of F is finitary, and together with pointwise addition. And so this definition here is exactly Ribenboim's GPA, okay, just expressed differently, given that all of Ribenboim's posets are examples of finiteness spaces. And here's our theorem. If you give me a monoid in the category of finiteness spaces and partial functions, and R a ring, and I don't need it to be commutative, but I do need it to have a unit, then R of M has the structure of a ring. And the multiplication is exactly the same as Ribenboim's multiplication. And the point is, for this to be well defined, I have to argue that the set X sub M of Fg is finite. And here's the argument, and it's going to follow directly from our definition of finiteness space. And so this is one of those things you need to stare at for a few minutes, but the point is the support of F cross the support of G, that is a finitary subset in M tensor M. Because remember, the finiteness structure on M tensor N is defined by taking all the squares, which are a product of a finitary thing which is the product of two finitary things. So this support of F across the support of G is finitary in W. And mu inverse of M is cofinitary. And why is that? Because singletons are always cofinitary. They're always finitary, and they're always cofinitary. And so the inverse image of that singleton is a cofinitary set. So X sub M of FG is in fact precisely the intersection of these two sets, one of which is finitary and one of which is cofinitary. And so by the definition of finiteness spaces, this is a finite set. And so our multiplication is well defined and everything works out perfectly. Okay, everybody follow all that? Okay. And so lots of examples in the world. I'll just mention, I can mail notes in the slides if people want to look at some other examples. I'll just mention this one. You can get all the row finite matrices by this trick. You consider the positive natural numbers, and you take as your, you take as your finitary set all those, all those subsets such that for every n, there are only finitely many m's such that n, m is in W. So this would correspond to, depending on how you set it up, either every row has only finitely many non-zero terms or every column. And then when you do that, your U perp becomes those subsets which only finitely many n appear in the first component. And it's easy to check that that's a finiteness space. And when you apply Ehrhard's linearization to this, you get the standard ring of row finite matrices. Lots of other examples. So someone told me, and I will confess I haven't actually sat down and looked this up, but Puiseux series were something that was studied by Isaac Newton. This is what I've been told. I don't know.
Yes.
Who said that? Oh, it's true. Okay, cool. So Isaac Newton really invented finiteness spaces because this as a ring is an example of one of our linearizations of a finiteness monoid. That proof is non-trivial. I'm not going to do it, but it's in our paper. Okay, so that's the first application of finiteness spaces beyond just modeling linear logic. Now I want to run through another one. And so I mentioned that the appropriate notion of morphism between finiteness spaces is, for what our purposes, is a partial function. And an example of a partial function that comes up all the time arises from groupoids. So functional analysts tend to view a groupoid as a set with a partially defined multiplication. So the multiplication is only defined when the row of the source of one equals the target of the other. And so we're going to use that fact to come up with some more examples of linearizations. And these are going to be arising from topological groupoids. So a wonderful paper. So I don't do functional analysis. So the paper that I followed to write these slides up is by Sims, and it's called Hausdorff et al. Groupoids and their C-star algebras. Pretty much all the groupoid ideas that I'm about to present come from there. So a topological groupoid is just an internal groupoid in the category of locally compact Hausdorff spaces and continuous maps. And we'll say that a groupoid is, such a groupoid is a tal if its domain map is a local homeomorphism. And I just mentioned that this implies that the range and the multiplication are as well. Okay, and so one of the things that, that functional analysts do is they assign to such a groupoid a ring, a star algebra, in fact. And here's the setup for doing that. So suppose I have an italic groupoid, and suppose that for all for all objects X in the groupoid, I'm going to define G sub X and G super X to be all those arrows for which the domain is X, and then G super X is all those arrows for which the range is X. And so the theorem is, if your groupoid is atal, these two subsets are both discrete in the subspace topology. Okay, and then I'm going to consider all those functions from my groupoid. And now I'm thinking about this the way the way functional analysts think of a groupoid is just a set with an operation on it, a partially defined operation. So I'm going to say I have a function f from g to c such that the support of f, so again, the support is all those values of, in this case, g, for which f is non-zero. And if you give me two of these guys, I'm going to define f times g as a new such function by this formula here. So f star g applied to gamma is, I find all those pairs alpha and beta such that alpha times beta is equal to gamma. And that is going to turn out it to be a well-defined multiplication. Excuse me a sec. And just as in the last case, I need to prove that this multiplication is well-defined. So in particular, I need to prove that this sum is over a finite indexing set. And this is just some topology. And so, as I said, the key is showing that the sum is finite. And here's what you do. You show that this set is going to be the intersection of a discrete closed subset and a compact set. And just by standard topology, that's going to be a finite set. And that all works out fine. So that gives me a nice algebra that I can assign to every atal groupoid. And so when we saw this little section in Sims's paper, we immediately said, hey, this finiteness basis should work here too. And it's going to turn out they, in fact, do. So this led us, as I said, to the obvious question. Is there a class of spaces for which I can define a finiteness space by the following structure? So I'm going to define my U to be all those relatively compact subsets of X. And relatively compact means its closure is compact in X. Because remember, or maybe I didn't say this, but your finitary subsets are downward closed. So if U is contained in V and U is finitary, then V is also finitary. So I can't say the compact sets, but I can talk about the relatively compact sets. So all those guys for which the closure is compact in X. So is there such a space where your U is going to be the relatively compact sets and your U perp will be the discrete closed subspaces? And it seemed, based on reading Sims's paper, that a pretty good conjecture would be that this always works when X is a locally compact Hausdorff space. And if that were the case, that would be a really nice result, because it's, you know, that's a huge class of spaces. It gives us a nice connection to that functional analysts would be interested in. It gives us a more intrinsic way of explaining why that sum is a finite sum. So this seemed like, to me, like a pretty good conjecture. So what happened next is I had a student named Joey Bove-Feistauer who was doing a summer project with me. And he came into my office one day and he told me what he had been working on. And then he said, hey, Rick, what are you working on? So I told him about finite spaces and I told him this conjecture. And unbeknownst to me, he went off and grabbed a couple of his friends and they locked themselves in a room for a couple of weeks. And a few weeks after that, Joey came into my office for our next meeting and he said, remember that conjecture you told me about? And here's what these guys proved. So this is Joey Bove-Feistauer, Ian Dewan, and Blair Drummond. All three were students at University of Ottawa. Conjecture is completely wrong, horribly false. The easiest counterexample they came up with is if you take the smallest uncountable ordinal, give it the order topology, then it's locally compact and it's Hausdorff, but it is not a finite space under the above. So that kills that. They did come up with a smaller class of spaces which does work. And I think everybody agrees this is not the best possible result. It's certainly not necessary and sufficient, but it is a pretty good condition. And that is this. We'll say that a topological space is sigma compact if it can be covered by a countable family of compact subsets. So what we're doing really is we're building in a sort of finitary structure into X. So this, as I said, isn't really the optimal possible result. And then we'll say that X is sigma locally compact if it's sigma compact and it's locally compact. And these three guys also managed to prove that if X is sigma locally compact in Hausdorff, then the above structure is a finiteness space. But as I said, it's not optimal because there are examples that don't satisfy that, but which are finiteness spaces. So that's where things stood. But now we at least have a pretty good class of topological spaces for which we can look at the corresponding groupoids and assign algebras to them using the previous ideas. And here I just argue that this is a pretty large class of spaces. So every CW complex with countably many cells is there. Lots of spaces are there, but it must be said lots of spaces are also not there. So here's an example of an important groupoid to functional analysts, which does satisfy sigma local compactness, and for which by the above we can get an algebra, a ring. And so this is Kumjian, Pask, Rayburn, and Renault. So if you give me a directed graph with V a countable set, and we're also going to assume that G is a row finite graph, where that means the obvious thing, then I'm going to take P of G to be the set of all infinite paths and F of G to be the set of all finite paths. Then P of G is a subspace of the infinitary product of edges, where E is topologized discretely. So that gives P of G a topology. Actually, let me just skip how there's an explicit description of the topology on P of G, but let's not worry about that. So P of G is the object part of an atal groupoid. And here is the construction for it. So if X and Y are such paths, we'll say that X is shift equivalent with lag K if there exists a capital N such that X of I equals Y of I plus K for all I greater than or equal to N. So eventually, X and Y are the same up to a shift of K. And then I'm going to define, so this is just properties of this shift equivalence. I'm going to define G to be, so this, now I'm defining the arrows of my groupoid. So an arrow from X to Y is going to be a K such that X is K equivalent to Y. And I can then define a multiplication in exactly the way that you would expect. So if you give me two such paths, then I define the operation this way. Okay. And here's the theorem. If you give it the topology as I described up 2 slides, then this is a sigma locally compact Hausdorff topology on G. And so we can apply our ideas from finiteness spaces to this topological groupoid and thereby get a ring. But I'm actually getting slightly ahead of myself because if you give me 2 topological spaces and they both satisfy the finiteness property, then, and you give me a continuous map between the two, a partial continuous map, I should say, then it may or may not be the case that the partial map may or may not be a map of finiteness spaces. So I need to add some extra structure here. I need in particular to say, I need to find a property for which the continuous partial map is a map of the corresponding finiteness spaces. Here's just a counterexample. Constant functions obviously don't satisfy that. And so here's the property that I need. I need F, so I have a partial function from X to Y. We'll say that it's continuous if it's continuous when restricted to the domain of X, given the subspace topology. And I also need that map to be locally injective, where that means the obvious thing. And here's the theorem that I need to make all this work out. So I have a continuous locally injective partial function between two spaces such that Y is T1, the domain is closed in X, then F induces a morphism of finiteness spaces where I take as my finiteness structure the relatively compact subsets of X. So everything works out fine. And the theorem is that works. G with its, so the previous G by those four authors, with its relatively compact structure is a finiteness space. The multiplication of the groupoid makes it a partial finiteness monoid. The linearization process gives us a K algebra, and K, if K has a star algebra, then I also get a star algebra. A big question that we don't know the answer to is, what's the relationship between this algebra that we just constructed and the algebra that functional analysts construct? And we don't really have any results on that at the moment. But it's a subject well worth studying. And I should say this groupoid, it's not a single groupoid, right? There's one for every row finite infinite directed graph. So there's actually lots of examples that we're capturing with this structure. And so I think that's a project that's worth following up on. But a good question, first of all, would be, what kind of topology do we get on this algebra? Because the algebra we've constructed so far is just discrete. And it's going to turn out there is a topology that we can use. And I think this is the last thing that I'll do, is just tell you how Lefschetz topology works. And I already mentioned the motivation for this. So you want to build infinite dimensional vector spaces with some topology such that the second dual space will have been cut down in size enough where we define a dual space to be the linear continuous maps, such that the second dual space will be just the right size so that that map is an isomorphism. And these were introduced by Solomon Lefschetz. And I don't really know what Lefschetz did with them, but these work exactly as we want them to. So a vector space is a Lefschetz space if it's equipped with a T0 topology such that, so obviously it has to be a topological vector space so all the operations are continuous, but here's the extra bit that you need to add. 0 has a neighborhood basis of open linear subspaces. And this you need to think about for a minute because it's kind of a strange property. So such spaces are locally convex, clearly, but they're kind of strange from the point of view of functional analysis. So in particular, every finite dimensional vector space has one Lefschetz topology on it, and that's the discrete topology. But there are lots of interesting infinite dimensional examples. And so what Barr showed is that this is a symmetric monoidal closed category. The tensor product is the usual tensor product of the underlying vector spaces plus an appropriate topology. And here's the nice result. The embedding of V into V star star is a bijection for all Lefschetz spaces. So that particular notion of duality does indeed cut down the second dual space to just the right extent that you want. But notice I didn't say is an isomorphism. It's entirely possible that the inverse map will not be continuous, but that's solved by just throwing all those away. So we'll define R-Left to be the full subcategory of reflexive Lefschetz spaces. So those objects for which rho is in fact an isomorphism. And the double dual functor is it left or right? Left adjoint to the inclusion functor. So you use the double dual to build reflexive objects. And so Barr showed that this is a star autonomous category, and R-Left is a reflective subcategory of the full category. And this is in fact one of the 2 or 3 examples that led Barr to write down the definition of star autonomous category in the first place. So this is one of, so as I said, this is one of the primary motivations for the definition of star autonomous category. Phil and I proved full completeness, which is a very strong form of completeness. It's essentially completeness with respect to proofs, not just provability, in a fragment of linear logic by using dinatural transformations on this category. There's a commutative version and a non-commutative version as well that you can get a topology for, that you can get a full completeness theorem for. And so here's what I'll finish up with. Our rings that we built using finiteness spaces can all canonically be topologized with a Lefschetz topology. Here's the definition, and it's not very edifying to look at. I wish I had some intuitive way of helping you think about what this is, but this works. And it does, in fact, give you a Lefschetz topology on the ring. And this determines a neighborhood basis at the point R of X, and the topology is a Lefschetz topology. Thomas proved some nice results about this topology. So the fun one is the last one. So a series will converge in this topology if and only if the limits of the individual terms go to 0, which is exactly what every calculus student I've ever had thinks. In this case, is actually the truth. And so an interesting question is, what about the completion of these topological rings that we get? And so Thomas proved that R of X is always complete. In other words, every quotient converges, but we have actually a slightly stronger version of this theorem. So a pre-finiteness space is just a set X equipped with an arbitrary U that doesn't have to satisfy that U perp equals U. You can still do all the above stuff. And our theorem is that R of X will be complete if and only if XU is a finiteness space. And so therefore we can think of this map as being a completion. It's obviously very different than the C-star completion that functional analysts think about. So what precisely is the relationship between these two? And I don't know the answer. And the other last thing I'll mention is that Christine Tesson and Thomas Ehrhard proved all sorts of computational properties using linear topology, properties of various extensions of lambda calculus. So what do their results say when we think about them in the setting of these topological groupoids? I think that's probably a very interesting question, which I don't know the answer to. I don't even have any vague conjectures on. And I think that's where I'll stop. So thank you all for listening.
Okay, thank you very much. Let's see, let's put everybody
Go. Leave the slides up or stop sharing.
Oh, yeah, no, he wants to still share. You might want to show some of the slides.
Okay.
Anyways, any questions?
I have to go. Bye-bye.
Okay, take care, Phil. Any questions? Any discussion? There's in the chat, Mio is saying something.
I'll look at the chat. Oh. Oh, nice. Okay.
Anybody else? Anybody else? Anyways, Rick, thank you very much. It was
Thanks all for listening.
I just have to ask, this is probably easily answered, whether this finiteness spaces together with the partial maps is a restriction category in the sense of Cockett.
Oh, I didn't check that, but I think it has to be.
Has to be.
Think, yeah. Yeah. That's something I obviously should have checked. Don't tell Robin that I didn't.
Well, I thought that was a good Canadian question.
Yeah, exactly.
Anyways, if there's no more questions, I think we should thank the speaker again, and we'll see you. I don't know if we have a talk next week. I don't remember, but anyways, I'll send out an email. Okay. Okay. Thank you very much. Good night, everybody.
Thank you. Thank you.
Take care.
Thank you.